Okay.
I think it's important.
Yeah,
And
yes.
thanks for hosting this seminar. So
Yes, is
the university where you're located is in Taipei.
no, it's in Doliu. Is not in Taipei. It is in
Yeah.
Doliu. It's 200 kilometers from Taipei. 1 hour
Okay.
by high-speed train.
It is in
Okay.
the
Very
middle
good.
of Taiwan,
Yes.
or
Okay.
a
Very
little
good.
bit to the south. Yes.
Yes, Dr. Wong is our director here of our research
Yeah.
center.
Hello.
Nice to meet you.
Nice to meet you, Dr. Dapper.
Yeah.
Okay. Very good that you organized this thing. I mean, congratulations
Yes,
for this
is an
big start.
initiative that we are still progress, and hopefully that we can have along the semester very interesting talks that can help to disseminate AI
Yeah.
throughout our community.
Definitely.
Okay, now Miss Carol, are you hearing me? So maybe we could start and please record our webinar, okay? Do
Yeah,
not
sure.
forget.
We have get ready our yeah.
Okay, so let's start. Okay, now it's 4, just to meet the schedule. So hello everyone. Thank you all for attending this AI webinar, which is hosted by Future Technology Research Center, National University of Science Technology here in Taiwan. Actually, we are planning to organize a series of AI webinars along the semester. And uh, our first webinar was held in June, but we had a break during July, and now we are returning to these webinars, and we expected to have around 2 invited talks per month, okay, which means a talk every 2 weeks. The talks will basically focus on, as the theme says, you basically focus on different aspects and applications of AI, and will be presented by renowned researchers of our community. So please keep an eye on it. And before introduction, our speaker of today, let me provide some guidelines of our webinar. Okay. First of all the presentation will be recorded. Okay, and will be made available in our website. So for those who wants to download both the slides and the recorded video, okay, you can go through our website. I will write in a key AI box the link, and you can get it. Okay. And during the webinar, I asked for everyone mute the microphone, okay, and turn off the camera. And if you have any questions, obviously you can use the key AI box for submit your questions. And everyone are encouraged to provide and to request any clarification of the webinar, so that at the end of the presentation we can have a very interactive discussions about this very interesting theme. Okay, so for today, I'm pleased to welcome Dr. Merwan Deba as the speaker of our webinar. And actually, it's a great pleasure for us to have you here, Merwani. And thank you very much for agreeing to give this speech today. The title of the talk is a very interesting, especially for 6G networks. It's entitled Native AI Networks. Okay, so we have a very, I confident we have a very informative presentation, and so that it can guide us in our future works, research works. Also, I'm confident most of you know you, Merwani. Actually, you do not need the introduction. So you have contributed a lot to our community in many ways, not only through your very strong publication records. But as part of the protocol, let me try to summarize your long biography, okay? So Dr. Deba, he served the master and PhD degrees from the École Normale Supérieure de Paris-Saclay in France. He was with Motorola Labs, Saclay, France, from 1999 to 2002. And also, he was with the Vienna Research Center for Telecommunications until 2003. From 2003 to 2007, he was an assistant professor with at the Biocommunication Department, Institut Eurocon, in Sophia Antipolis, France. In 2007, he was appointed full professor at Centrale Supélec in France. From 2007 to 2014, he was the director of the Alcatel-Lucent Chair on Flexible Radio. From 2014 to 2021, he was vice president of the Huawei France Research Center and jointly the director of the Mathematical and Algorithm Science Lab, as well as the director of the Lagrange Mathematical and Computer Research Center. And since this year, he is a chief research officer at the Technology Innovation Institute in Abu Dhabi, where he leads the telecom and AI centers. Dr. Deba is an IEEE fellow, is a WWR fellow, a RACIP fellow, Institute Laws Bachelier fellow, and a member emeriti SEE. And his research interests lie in fundamental mathematics, algorithms, statistics, information and communication science. And he has received multiple awards for his contributions. And if I would tell here all of them, I would spend much time. So now, without further ado, Dr. Deba, the floor is yours.
Thank you very much. So Daniel, you see the slides now? Yeah?
Yes. Perfect.
Very good. Okay. So first of all, thank you for the invitation. I'm very happy to be able to give a talk. It's quite unfortunate that some of you are during their vacation and plugging in, but I really appreciate the time you're taking to listen to me. I'll try to be as deductible as possible so you can grasp a full understanding of what's happening today with the application of AI to networks, but also the use of networks for improving AI. And I think this is a big game changer that we're seeing in the telecommunication industry at the moment. Of course, one of the applications is around, as it was said, 6G. But of course, these techniques are already implementable and implemented, by the way, in actual networks like 5G, for example. And so as far as I'm concerned, I'm a specialist of, let's say, wireless in general. Been working a lot on 4G, 5G, and today 6G. And also, and I'll explain why, I've been working since more than now 4 or 5 years on the AI because I was quite skeptical at the beginning due to my background in mathematics. But it turns out that something happened during the work that I was doing and that triggered a high interest on my side related to that. So as far as I'm concerned, I am now a chief researcher at the Technology Innovation Institute. The Technology Innovation Institute is a public funded research institute that just started right now. In fact, it started 1 year ago, but the progress has been very fast, which is like a global hub of innovation right here in Abu Dhabi in the UAE. And it's sponsored by the Abu Dhabi's Advanced Technology Research Council. And the aim, of course, is to foster within the region here a more global knowledge economy or a knowledge-based economy. Research Center in the general topics related to technology, going from quantum communication to drones, to materials, to directed energy, to cryptography and security, to, of course, telecommunication AI, but also biotech, another domain. So it's quite big at the moment. It's increasing, and it's going to have, as far as I'm concerned, and this is one of the reasons I joined this institute, quite a huge impact in the next years within the industry that we're facing at the moment. And the idea, of course, is to foster basically a better world by pioneering the most advanced innovation to solve the society's greatest challenges. And as we were talking before with Daniele, as you can see, the question of sustainability, for example, is one big question that is harming us at the moment. But there are many questions that need to be solved at the society level. Of course, we work at the same time on what I call business-driven research, meaning trying to solve existing problems. Technology-driven research in the sense that building roadmaps which are more related to, let's say, things which will happen in the next 6-7 years, where we create the problem and solve basically the problem. For example, 6G is one of them, but also vision-driven research in the sense that we also try to solve some long-standing problems that have been there and for which we need to provide some solutions. Typically, explainable AI, for example, is one of them. Our objectives are threefold as far as TI is concerned, is to attract the brightest scientific minds. So for people who are just now graduating from their PhD, they're quite welcome to write me an email if you're interested to join and send me your CV so we can have a discussion. To help the society overcome its biggest hurdles and to become a world-leading research and development institute around that. The approach of research that we do is quite simple. We start defining a research roadmap with use cases. We also try to look at who's leading that domain in the world to be able to start collaborating with those, or if it's internal, that we'll be doing it on our own. We identify the academic partnerships, and universities like yours are part of our network, and we would be extremely happy to continue and collaborate and start collaboration. Then, of course, on top of that, we have tried to also attract talents to work within this project that we have identified, and then we start allocating the right budget to foster basically a domain of research related to what I was saying. And you can see here, you have a lot of incentive in terms of coming here. The first one is that for people who are in academia, we want them to keep their current university affiliation because we think that the dynamics which are within basically the exchanges that you have between a research institute like ours and university is extremely important in terms of exchanging basically IDs and students and also recruiting. We also have basically research funds which are quite important to foster our roadmap. The same thing for basically allocating those budgets. We encourage highly people to do publications, basically, and be able, of course, to have a dissemination of their work and have a high impact. And we try to work closely with all the groups in the world. And also the conditions in Abu Dhabi are quite nice in terms of living for the people who would like to join our researchers. I think I gave you quite rapidly the kind of institute that we're trying to build here, which is not a company, which is not a university, but it's really people doing full-time research all the time on basically some very challenging problems. And we're looking for the brightest minds, and so that they can, of course, blow their mind and work on very interesting problems. And of course, I'll be very happy also to collaborate with those who are coming here. Now let's go to the focus of my talk. I'll be doing three things. One, the talk was called Native AI Networks. I'll do an introduction because I'm not sure many of you have the full grasp of what is AI. So I will do sort of a crash course, which is going to be extremely rapid about the general IDs. Even if you don't know nothing, you'll see that I will rapidly introduce you the concepts, and I think you'll be quite familiar, and you will understand why it has become so important. And then I'm going to explain two aspects which I think are very important in native AI networks. There's one part which is what we call AI for networks, meaning using what we call here the AI technology to improve the performance of the network and improve basically the boundaries of communication or networking as we know. Second thing, which I think is much more important than the first, is us as telecommunication, I would say, engineers, researchers, what are the right protocols that we're going to build to be able to connect the various AIs which we're building today. As you know, AI is becoming very pervasive in the sense that you have now AI at the same time on the edge, on the fog, and on the cloud. And basically these AIs, or what we call intelligence, needs to talk to each other. And to talk to each other between AIs has become extremely important. The various, I would say, system that we have been building is mostly about connecting basically either people or things. Things here meaning things like IoT, which are dumb devices for which there's no basically some kind of mechanisms of intelligence embedded so that you can basically do some kind of proactiveness in how you do. In general, things or the way these things behave is quite defined with some use cases. And I think this is a big game changer. And this is, I think, where the biggest potential is going to happen, and especially for 6G, where we're going to move from a world which is going to be more about connecting things to what I call here connected intelligence. So I think you're quite familiar, first of all, with the G waves. If you look at the G waves, what we call the generation, G means generation here. I think for you, you're quite familiar with what we call the 2G, 3G, 4G, 5G, and in the future, 6G. If you look at basically, I'm not going to talk about 1G, which was more an analog, but all of you know that the 2G system started around 1990 up to 2010. We have now a lot of 2G networks still existing, but basically the market is very narrowing down, and we have even some 2G networks which are closing. They're not closing directly because, as you know, you still, when you do your payments with your credit card, we use in general GPRS, and this is still, you're not going to put the 4G or basically some kind of narrowband IoT for that thing to be built because it's over dimensioning and GPRS works. So there's still a bit of a market for that. But roughly, the 2G market was built on what we call mobile for voice, meaning having a seamless handover where you move around. Of course, having wireless voice is not a problem. You do it at home, you have DECT system. But the 2G system was extremely smart in building basically a worldwide system providing mobility for voice. Of course, since it's more than a 20-year time frame, the engineers build it so now we have SMSs and other things like that. The technology behind is very different from the generation. 2G is mobile for voice. Behind you have what we call technologies, which fulfill those requirements of mobile for voice. Of course, the most famous one is called GSM, but you have other systems in Japan, in the US, which also fulfill this requirement. If you go now on 3G, the big target of 3G was what we call mobile for data. It started in 2000, it continued until 2020, and now you have also some 3G networks which are closing down, not totally, but there. And the idea was to provide data for mobility, okay? Behind, of course, there are several technologies which fulfill that. You have to separate the technology from the generation. The generation gives you here mostly about what we call the KPI or the requirements, and then you have various technologies that can fulfill that. Same thing around 2010. One of the focus was to provide mobile for internet, meaning having some kind of wireless ADSL experience in outdoor mobility. And you have, for example, two technologies that fulfill the 4G requirement. You have what we call WiMAX, which did not have the expected success that we wanted, and you have basically the classical LTE, long-term evolution, with all its basically 4.5G and all the other aspects that fulfill those requirements. By the way, this is quite important. We were so focused, and I'm going to insist on that because this is what triggered my interest in AI. We're so focused in 4G to have mobile for internet that voice does not work so well in 4G. What we have is some system called voice over LTE, which is a kind of voice over IP, because voice in 4G is not a technology, but it's more basically an application. And of course, it took us a lot of time to be able to provide the same kind of what we call quality of experience that you have in a 2G network on a 4G network when you make a call. And you have to know that the initial deployments that we did for the 4G system, usually you had what we call a CS fallback. It means circuit switch fallback. It means basically that when you want to make a call, you go on a 3G system. And when you want to browse on internet, you're on 4G. Now, of course, in many cases, we have solved that, and I'll talk about it. And AI was instrumental in improving basically the performance of voice over LTE. 5G came in, mostly target for mobile for things, with all these latency requirements, things like that. But we're talking here about mostly about machines or things which do not have any kind of embedded. And now one of the big targets that we're looking at is mobile for machines. When you have basically, of course, these objects for which you have computing power in them, and you have processing power, and you also embed them with intelligence, and where you want to connect that intelligence. And this is one of the big hype today, and how to do it is a big question. And my talk here is going to try to solve some of those questions that we're talking about. Now, if we want to go on these mobile for machines and want to solve them, this is a classical thing you would do if you're doing a PhD. Well, you would do first some kind of state of the art, and you're going to look at the past and say, what is basically the status of the science before I start my research? And this is the way we do it, and everybody does it. And this is what I'm going to do it now, what I'm going to do now. So if you go back in the past, you're going to ask, who were the first people of looking at the intersection of AI and networks or communication? Of course, everybody brings Turing, but it's mostly about computers, computing architectures of computers and AI. Here I'm talking about the conjunction that I'm willing to do between AI and networks. And this goes back to a nice paper of Shannon, published in 1950. Basically, as you know, there were two landmark papers in 1948 of Shannon. Of course, they were done much earlier in the years when he was at Bell Labs during the war, but these papers were declassified around 1948. But then he published a nice paper in 1950, and as you all know, Shannon was also a big, what we call, chess player. And within chess, you feel this intelligence. In that paper, he was asked to bring his vision about what's next. And the next, if you read it, it's quite interesting. He talks about machines and the machines that would do things that humans do, and especially networks. And one of the first things that he proposes is machines for designing filters and equalizers. This is exactly what we call AI, the physical layer today, where people are trying to use AI to find back the MMSC equalizer and all these things. Machines for designing relay and secret switching circuits. This is what people are doing today related to the routing problems. Machines which will handle routing of telephone calls based on the individual circumstances rather than by the fixed patterns. This is also some big trend today that is happening. Machines for performing symbolic mathematical operation for computing, of course. Machines capable of translating from one language to another. All the NLP community is heavily investing their time on that. Machines for making strategic decisions in simplified military operations. Machine capable of orchestrating a melody, and machines capable of logical deduction. So all the ingredients were there. And so if you look at that paper and you look at the end and ask why he didn't move forward, well, if you read that paper in detail, he explains clearly the computational power available at the time make it that if you try to apply those techniques right now, it would take you a huge number of years to find a solution. And so there's been a big change, and we'll talk about it, that made it happen today. What could not make what was not possible many years ago. Second thing also that Shannon was proposing is not the AI for network part, but the network for AI part. In the sense that, well, the big paper that he published in 1948 was related to what we call level N, level A, Shannon theory. Meaning that what you want to know is if you want to design a system to send some data from one point to the other point, your question is how can you reconstruct basically that data at the endpoint accurately? This is called level A. Second that he proposed was level B communication, which means how precisely do the transmit symbol convey the desired meanings, the sense, the semantic that you're doing in communication. And of course, this was an open problem. And this, of course, is something else because you want to build a communication link where basically you have a context which is built between different AIs because the AI system has been bringing a lot of data. With that data, there's a context which has been built. And if there's a context, the way you communicate is totally different. It's typically our case. When we talk to somebody, the more we talk with somebody, the less we need to transmit bits. Why? Because we don't need to restart the communication every time from scratch. The legacy of the number of years makes it that there's a memory, and we learned a lot of things with our intended receiver. So basically, we don't need to say much to have the same impact. And the way you build this is extremely important. And this is also something that Shannon proposed, but he didn't really touch upon it. So that paper, he explains the ID. But then, of course, how you do it is a big question. And we'll talk also about this big trend today that is happening around networks for AI, or the semantics that you can embed in the communication to be able to transmit. Next big shot around 1948 was, of course, Wiener. As you all know, Wiener, Shannon is the father of information theory. Wiener is known as being the father of what we call the signal processing world. Of course, Wiener at that time did a lot of things. Quite impressive in the sense of building radars. He's at the heart of all the framework and the theory around the match filter for radars and things like that. But he wrote a nice book called Cybernetics and Control and Communication, the Animal and the Machine. And his idea was to say the following, is that the Shannon model that was built in his paper, the 1948 paper I'm talking about, was related to, you had a model of your link and for which you wanted to build basically a communication system. You made assumptions on that basically black box and basically especially some kind of stationarity or ergodicity principles. And you were able to induce some kind of limit on how much information you could transmit, which is related to the capacity. Now, in many cases, it's not possible to have a model. Okay, the black box, you have no knowledge about it. And if you have no knowledge, what you're going to do, you're going to learn it. And how you're going to learn it, you're going to do it through a process called feedback. So by the way, the slide is in French. It's not because I'm coming from France. It's typically, that's quite surprising, is exactly extracted from his book, because he took a French publisher to publish it. And what you do is that you're going to do some kind of loops with a feedback process, where you're going to shape your input with a certain, what we call, target output. So you're fixed basically your target. At that time, the target was called the MMSE, the minimum mean square error. And you're going to do basically these loops to be able to do it. And of course, this is related to a field which had a lot of impact, called control theory. By the way, a lot of people today in the AI field are working on control with AI. But basically, the idea was that you would be able to prove a lot of convergence properties, basically, if you start looking at this problem of learning and going. And in fact, the learning is extremely interesting, because this is something that around 2000, a lot of communication engineers started to develop, especially within the realm of what we call femtocells, small cells, and within the realm and a nickname called SUN. SUN means self-organized network. And the idea basically is that you have players within what we call a game theoretical setting, and in which basically a transmitter will transmit some data, and then we'll have a feedback with the ACK-NACK, acknowledgement or non-acknowledgement, about what he saw. And then you will change basically your strategy so that basically you could, once again, find the right level of transmission. Of course, the problem that you have with that in general is that when you are in a mobile environment, you have what we call an exploration phase and an exploitation phase. The exploration phase should not take you too much time, because if you start taking too much time to learn, by the time you have learned all the parameters of your problem, it's too late to exploit them. And so in mobile environments, you have to be extremely careful how to design a system which works on those principles, where basically you have this feedback coming out. And then you have also some issues which are related to the fact that you want a system which at one moment stabilizes, in the sense that you found the right parameter, and you don't want to deviate from those optimal points that you have defined. Okay? And the problem of stabilizing is related to a notion in mathematics called equilibria. And it turns out that also when you start playing with those mathematical concepts, the convergence is not always proved, or you don't always achieve it. You always only achieve it in some cases, especially in the cases where you're looking at some utilities function. Utility here means bit rate, capacity, whatever, which has some nice properties. These properties in general are what we call convex properties. If it's not convex, it doesn't work well. Of course, mathematicians and engineers know how to convexify functions. The way they do it is that they take the expected value. Because whenever you look at an average utility, well, basically you convexify that function, and then you can prove a lot of things. When you don't have this average, it doesn't work. Now, the problem, of course, in communication is that nobody's interested in an average rate. He's more interested in an instantaneous rate. Why? Because if I have on average 10 megabits, but I don't have at all any kind of data during the whole week, and then I have 100 megabits, I'm not happy in general. What I need is a minimum. But in any case, just to tell you that we have built these systems, and basically these are all the kind of algorithms which were used without no one talking about AI or machine learning. Best response dynamics, reinforcement learning. There's no notion here of deep. Deep here means in the sense that you accumulate a lot of data based on what you have learned, and you use, of course, all these what we call deep reinforcement learning algorithms to do it. But you just use reinforcement learning, and reinforcement learning has been used. Now, you can tell me why it didn't work. As I told you, one of the reasons it didn't work is that we implemented those systems in the self-organized networks. And one of the reasons is that in general, in wireless, the convergence time is too high compared to basically the request you get. And so, although within the SUN until 2012, a lot of people jumped on these things, they stopped a bit quite rapidly, because it turned out that it didn't work as we expected. Although a lot of people with expertise in game theory in all these problems of learning we're going forward. But I think it's very important to have in mind that already the notion of learning with distributed systems in wireless was already there. And you can look at all the papers that people have been publishing, especially in the game theoretic setting, in showcasing basically how a system could work. Now, what's the difference today with all the works we did before? Well, the difference today is that memory and computing has become cheap, meaning that basically, if you look at the 1948 Shannon model, you don't have any kind of memory. What it means that you don't store data, you throw it every time you communicate, meaning every time you communicate with somebody, well, basically it is as if it's the start of a new adventure of communication with that guy. Now, the fact that you accumulate a lot of data related to your communication, you start building some kind of context with your intended receiver. And then you have also the capability of computing directly on the TX or RX of the information. And of course, if you start doing that, it moves a bit, as I told you, the things, because at the end, you have some AIs that you want to connect between them. And if you have AIs that you want to connect, well, it moves your realm of communication from connecting things to connecting intelligence, and moving from what I call here a Shannon 1.0 perspective to a Shannon 2.0 perspective. And this is going to be one of the part of my talk around using networks for AI, which I think is going to be a big thing, and which is able to happen now. The other thing, of course, that makes it that now we have some ingredients to re-look at basically the statements that were made in 1948, is that there has been 3 game changer from my perspective. The first game changer is basically the massive amounts of data that can be used today with machine learning, that meaning the storing capability has changed. The computing capacity, which is also completely realistic. Here, of course, as I was talking before with Daniele, is that, of course, we're not taking into account the green aspect and the energy aspect. And I think this is going to be a big hit in the next years. And we'll see that the amount of energy that is poured in to solve some problems has become not any more sustainable. And the last one is what we call the machine learning algorithms, which have become advanced. Said that, as you all know, AI is not new. It started already with a quite famous conference in 1956. It moved very rapidly afterwards. Then there was what we call winter. Another then came in with what we call expert systems. Some of your PhD advisors have been very intense workers on that discipline. But then we knew another winter. And the 3 ingredients I'm talking about made it that we had an explosion already starting 2008, which is now continuing, which can get, as I told you, another winter, which is going to be the energy winter from my point of view, in the sense that at one moment we will be reconsidering the amount of money that it costs us, just like, by the way, all the technologies that we're inventing today. If you look at the technology that we're inventing today, they're taking, in some sense, for granted, basically, the energy that is consumed. Take Bitcoins, blockchains, for example. Today, the amount of energy that is poured in Bitcoin is totally realistic to basically the gains that you have when you do mining. Mining today on a worldwide scale is at the level of what you would consume in Ireland, for example, per day, for the mining per day all over the world. So it doesn't make things quite sustainable. But I think this is another story, but we need to take it into account in the next year. And of course, it got also famous in the last year with basically some breakthrough papers, which were done by these 3 guys, which received the Turing Award. Conferences, you have thousands of people trying to listen to them. And of course, they built up a very nice, I would say, framework, which I would call like the FFT, or the elements of what we need in AI, which are related to what we call the DNN framework. And I think you've been hearing them here and there everywhere, and I think this is going to be a big game changer. Now, still in my introduction, I gave you basically a historical, let's say, timeline about networks or native AI networks, and giving you a bit of sense that it's not something totally new and for which people did not really already see the potential. The second part of my introduction here is going to be more about explaining why it is important. And here, what I'm going to do in a very easy manner, without going into mathematics and the algorithms behind, I'm going to give you two very basic examples to showcase why AI is important. So suppose you need to do what we call a ballistic kick, meaning that you want to kick a ball at a given distance, which is a classical problem that you have when you're in high school. So way of solving it, which I'm giving this example, by the way, for a simple reason. Of course, it has some impact in wireless. This is called beamforming. You want to find the angle with which you want to kick or beam towards a destination where basically you know that it's on that side. And the question, of course, is what is the angle to which you're gonna launch your beam? Okay. So of course, doing that in general, you have two ways. One way is basically to look at all the problems of wireless communication, understanding the medium, having a good model of your environment, and being based on the channel acquisition to find the beam. Okay. Second is, in many cases, it's not possible to have access to that. And you're questioning yourself, how can I do it differently? So here in this example, you can do it differently. So here, if you want to kick the ball, you're 18 years old, you're at university, high school, you take Newton, and Newton provides you this classical equations with gravity, and you're able to solve and find the angle with which you can kick the ball at a given distance d. Second option is that you have no clue of Newton, so you don't have access to that theory. So how we do it, it's very easy. You kick the ball like hell, many times. So you generate a lot of data, okay? And you write in two columns, angle, distance. So 1 meter, 2 meter, and you have all the angles. And next time you're asked to kick at a given distance, it's very easy. You look at the table, it's a lookup table, and you look if the distance is there. So if, for example, you want to kick the ball at 435, you look at there, and if 435 is there, you can find basically directly the angle. There's no intelligence in this, okay? It's called data mining. It's been there for years. However, basically, you need to find some very smart algorithms to do your search, otherwise it will take you a lot of time. You're not going to do 1 meter, 2 meter, 3 meter until 435 meter. Otherwise, you're dead. So you're going to clusterize your data and say that 435 is in the class 400, 500, for example. Okay? Next point now, imagine that the distance is not there. This is where it gets interesting because you have sampled your space, but the distance is not there. So if the distance is not there, what would you do? You would do what we call regression, meaning you say 435 is a mix of 400 and 500 or whatever distances, and you're going to find what is the linear combination of the different distances, and you're going to be able to find what is the linear combination you're going to do in the angle domain, okay? It can be linear, it can be nonlinear, but let's start with linear. And you do the combination, you're able to find it. Now, doing that, mathematicians know how to do that. They know how to basically find the right spacing to do that. What's quite magic about the revolution about this machine learning, so here machine learning is not, there's no AI, it's only regression. And it's only what we call a functional approximation. You're going to find what is basically the x, if x is the distance with respect to the theta, or theta equal f of x, and you're going to find how to find basically the function f. Now, doing that, we have now today a very sophisticated mathematical framework. One way to find the function f, which relates these two domains, is to basically do some kind of expansion of your function. You say f, I will make some assumptions, suppose that it's bounded, then I can approximate it by a polynomial, and try to find those weights of this polynomial, which do that. And I can do the learning and find them. Another way, which was quite spectacular, is that some people find basically a hardware, basically architecture based on neural networks, where basically we have an algorithm which already finds you all the weights which can do this mapping and learn that function. So it's quite spectacular because you're able to directly basically train this black box, meaning put distances, angle, distances, angle, distances, angle. And next time I put a new distance, it gives me the angle by learning basically those weights based on the data that I have. So it's quite simple because you're doing what we call function approximation, and we have the hardware to do it, and we even have the framework to do it. This is what's even more astonishing is that some people build all the frameworks, call them TensorFlow, call them Apache, which makes your life simple. So in this example, what I showed you rapidly is that you're able to replace Newton with AI. you're able to replace Maxwell with AI. Imagine you learn or you have a lot of data corresponding to electromagnetic field in different position, and I ask you, what is the new electromagnetic field here? Okay? If you know nothing about Maxwell, you're able to still find it by doing some kind of linear regression of your system to find it. You can do Schrodinger. You can do nearly all the different, I would say, mathematical theories for which you have no clue. So it's quite magic. And of course, in our case here that I'm showing you is something that we tried in what we call the 5G massive MIMO beamforming. We beam for a given position, we beam for a given position, we beam for a given position, we beam for another given position. And next time there's a new position, by interpolation, but without doing all the hassle, I can find the right beam for a new position. So, and without knowing if it's millimeter wave, without knowing if it's sub 6 gigahertz, without knowing if it's something which is more dense, urban, or whatever, and it works quite fine. So it's quite magic, but let me just tell you that there's some caveats, and we need to know those caveats. Once you know those caveats, then you know the range of application of those IDs. The first caveat, of course, is that I went quite fast in telling you that there was a one-to-one mapping between distance and angle. In fact, it's wrong. The initial speed, the V0 that you see there, is extremely important when you solve this problem. In fact, there is not a one-to-one mapping. There is two inputs, distance, initial speed, and angle. And so when you're an engineer, or what we call a data scientist, it's not easy to know what are the columns you need to use to solve this problem. And this is in general the problem of a data scientist, where he spends a lot of time trying to add new columns and trying to find which are the columns to take into account, and can become a big hassle for our communication engineer. It is as if I told you, suppose you have the RSSI on your mobile phone. Can you find me the load of a base station based on the RSSI? So even if I give you a lot of columns, load RSSI, load RSSI, load RSSI, okay, you will not be for a new RSSI to be able to find the load. It's not possible. There's other input parameters. It is as if I was telling you that you're a data scientist working in a health company, and then you have a doctor coming to you and telling you, oh, here's the column of the blood pressure, and here are the candidates of cancer. You know, we relate them. I give you new blood pressure, tell me if he has a cancer. As a data scientist, you would say, okay, I will work on it. But then if you have a bit of insight of the domain, you would say, no, I would need also not only the blood pressure, but also the historical data of his parents and stuff like this. And it's not easy to know that, and you can spend a lot of time trying to work out. This is the first caveat. Second caveat of this technique is that suppose that you have optimized your system exactly for a given configuration. So here, imagine that you learned how to kick the ball when it was sunny. And the day you have to kick the ball, it's rainy and it's windy. So all the things that you learned, you have to redo it from scratch for every configuration. Imagine the amount of energy that you need to pour in to get just a single number on which you need to kick the ball. Of course, we have some techniques called federated learning, called transfer learning, where if you learn in a given domain, you can know how to extrapolate into another domain, okay? Typically, if you learn, for example, French, in general, you can learn faster Italian because there's a lot of correlation between French and Italian, for example, okay? But of course, if you speak French and you want to learn Arabic, the transfer learning does not work because there's not so much connection between the two languages. And so we can use that. And typically in wireless communication, it would mean that you have learned how to beam basically in a city like Beijing. And then you want to go and learn how to beam in a city like Paris. So if there are some correlation in terms of how the structure of the buildings are, things like that, then you don't need basically to retrain from scratch your beamer in Paris. You would initialize your neural network for the beam exactly at those parameters which were optimized in Beijing. And then you would add up the new data to refine, which is what we call not a random initialization of your neural network, but mostly more, you will initialize your neural network exactly at those points, for example, okay? But still, again, here you have another caveat, which is basically trying to redo things for every configuration, which you don't do in general when you have basically a model. And the third one, which is I think the most problematic, is that if you learn to kick on Earth, you have no clue on how to kick on the moon, because basically gravity is different there. And what it means that the way you did your learning is mostly about function approximation. You were not able to capture basically the real understanding on the data. And the real understanding on the data here is for you to be able to extrapolate the notion of gravity within your data. Now, gravity, when you look at gravity, it's what we call an invariant, meaning gravity does not change by making your data rotated, translating, okay? And which means that the techniques that we're using today for solving those problems are not using basically what we call topological structures. They're not using geometrical structure, so that you can learn the environment and extract basically what are the environment properties. And basically this is where you would invest your money. Of course, there's a big trend today of people trying to do that and looking at topological structures based on the data, trying to look at more basically the semantics between the data. It's still an open field, but it's moving forward, and which tells you that we are still today at the machine learning, which is based on correlation mechanisms, okay, and statistical mechanisms, and not trying to learn basically this topological structure, and which has to be the next step that everybody's trying to look at. Now, why these techniques got famous? Well, they got famous because it works, and one of the most known discipline where it works is, of course, what we call voice recognition. So many people in the 80s, and especially your PhD advisors, have been working in the 80s in basically trying to model here what we call the larynx, meaning how to model how a voice is emitted. All the people who worked on this in the 80s were never been able to understand how it would work. And voice recognition didn't work. The day voice recognition exploded is the day where we decided to stop modeling and see the problem of voice recognition as what we call a classification problem. You record many sentences with basically, of course, there are different features. And next time somebody says something, then you will try basically to classify and find in which class that sentence is and immediately find it. And of course, this works. It has been a big explosion in our community. And of course, now people are questioning on how to apply it, of course, for the image classification, another domain on which we have. And last point I want to mention on this fast crash course I'm trying to do for you in this AI is the problem of data. And the problem of data is extremely important because as companies, usually it's not the academics who have the data, but it's companies. Now you could say that companies are basically not playing the game in the sense that they're not sharing the data. In fact, many companies have no issue, and I know from my experience, to share data. It's not the problem of sharing the data. It's to share basically the IPR on how this data was generated, meaning the knowledge which is inside the company based on the engineer on how they created that data for the people. And this is, of course, know-how which is specific on the company. But the data itself is not a matter. And I can give you an example very easy. If you have data and nobody tells you how it was processed to given to you, you will take immediately false conclusions. So in general, giving you data is useless. We need to give you the data with the notice on all the different aspects of how it was generated. And this is a very nice example that I like to give every time I give a course, is the example which is typical. This is typically an airplane in World War II, which was going from England to France and bombarding basically the Germans and coming back. And the red dots, and coming back to England. And the red dots are basically the bullets, the shots that it got, okay? And the commander of the base in the UK at that time was saying to the statisticians, they were not called data scientists, well, you see, we have a problem because basically we have planes not coming back. Tell us where to reinforce the plane. Of course, the data scientists or statisticians at that time were working on that. And as you can see, the more there's red dots, the more they would put metal to basically try and reinforce to avoid basically that the planes get hurt, because on the statistics that they got, well, they got more shots exactly on those things. Then, of course, the pilot came in and said, no, you're totally wrong. You should basically put more metal exactly where there's no red dot. And one of the reasons you have to do that is what we call the missing plane problem. Many planes that did not come back were exactly shot on the cockpit, exactly where the pilot is. And since they did not come back, you're working on basically missing data that you did not have because you didn't know exactly what was happening. So you need to work with those guys, which are the pilots, which were basically working on that. On how it works. And this is, of course, the value of the company. Okay. Now, of course, to work out all these things that I was saying, well, the big thing which is behind is, of course, all the algorithms which are being used. And here you have a plethora, as you can see, of techniques which are today used related to what I'm saying, going from signal processing to data storage to computer vision, but also all the mathematical techniques related to spectral manifolds, to dense sparse linear algebra, and going to dynamic programming, which requires, if you want to do the research behind, a bit of expertise in those domains. But as I told you, if you're not going into more research, you have frameworks which enable you to do that. Now, just to end my conclusion, you have to know that today, the majority of people are mostly on the part that I was talking about, which is basically related to what we call here the single task intelligence, meaning building chipsets and whatever to do just one thing. And this goes to the framework. Of course, the big thing that we need to build by 2030 is basically all this strong AI perspective, and where you cannot go beyond basically the single task. And of course, the future, which is the big hype today, is be able to mimic as much as you can how we work in terms of energy. The amount of energy that we consume to get results is tremendously low compared to how chipsets work, which is called the superior AI in that thing. Okay, I think you got rapidly this course. Now let's go to the purpose of my talk, which is this intersection, which is going to be about AI for networks and networks for AI. So my first experience, and as I told you at the beginning, was related to the fact that I was very skeptical around AI. And one of the reasons is that I don't like the black box approach, in the sense that I'm more with the background of mathematics. I try to understand stuff. And one of the big issues that I had was a problem called voice over LT improvement, okay, when I was working a couple of years ago. And voice over LT, as I told you, is basically the way voice is implemented in LT networks, which is more about an application rather than technology. Now, it doesn't work well for a simple reason. I think you're all familiar with Skype and others, is that whenever you do voice over IP, well, the way information is processed, it goes through basically the IP protocol. Now, if you do a bit of communication, it's extremely hard to model basically the end-to-end IP protocol, because you have the wireless link. So even if you improve the wireless link, it doesn't improve directly basically the IP part, because it depends where the servers are, things like that. So I spend a lot of time trying to optimize through formulas, basically the voice over IP or voice over LT performance. And it was extremely complicated, because if you have an impact on one point, you destroy another point. If you change basically the location of things, then it's extremely hard, because it's hard to have a mathematical or objective function that you can optimize. And then, of course, my colleagues came, especially the colleagues basically from the wireless BU business unit, came with a lot of data. And when they came with a lot of data, they told me we have a lot of data for different configuration of a network and different voice over LTE quality. Can you, based on all this data, find what would be the new configuration or layout you have to do based to give a certain performance metric? And of course, this is extremely nice, because it's a regression problem. You need to link based on different, I would say, kind of sampling that you had of space, how you do it. And quite surprisingly, it worked. The improvements were drastic. It were drastic because basically for once, you had an end-to-end basically optimization without having the formula, but based basically on different data that you got. And this triggered a lot of interest for me, because at one time I said, I spent many years trying to solve mathematical problem. I never was able to do it. And here, for quite surprisingly, I'm able to do it, and the performance are quite huge. And so, of course, you see that this already triggers a different way of looking at the problem, which we call here AI in networks, where basically the classical network algorithm or wireless algorithm, the value is the link, where the scenario is mostly manually, where the target is about local determined optimization, where the scope is about local modeling, and where you try to tune the parameters. And when you go towards the AI framework, you're looking at the value, which is the data. The scenario is automatic. The target is about global property optimization, and the scope is end-to-end. This is extremely important, and all the problems that we're facing today are mostly about end-to-end. And where the method is about big data, and what's extremely nice is that you set the target, and it goes, and you run the system, and you go. Of course, you need to take into account, of course, the kind of granularity in terms of time scale that you need to take into account. Is it at the resource block level, or is it at the slice and whatever, depending on which you're working? And as you can see today, if you look at the wireless case, the kind of application is quite large. You have basically the AI, which is used for LTE power control, for high frequency, low frequency calibration, for high frequency map reconstruction, for basically PAPR, nonlinear compensation. Why? Because basically, well, you have a channel in which basically you in general decouple the FFT and IFFT from the channel. But then if you plug in the FFT and IFFT, you have what we call nonlinear channel. Many people try to tackle the problem of how you transmit in a nonlinear channel because of the fact that you have the amplifiers which saturate. They were not able. But the day you start modeling this as a black box, which is a nonlinear black box, and for which you try to find what is the right modulation format to transmit in this nonlinear by this learning mechanisms, you get some improvements which are quite drastic. And you can see some of my colleagues, ex-PhD students like Jacob Hoydes and others, who have been working quite intensely, for example, in that. Then you have, of course, related at a much higher level, related to basically the policy management, the comp mode selection and link adaptation, and of course also the AI management platform. And the kind of algorithms that are being used today go from regression, clustering, classification, to reinforcement learning, dynamic optimization, association rule mining, to deep learning, reinforcement deep learning, transfer learning, and graphical algorithms, for example. And also the kind of AI that is now being poured goes at the same time to things like network OEM, operation and management, to improving the performance limits, to also targeting new kind of businesses, but also I'll talk about it to things which are very physical layer in terms of research that people have been doing and for which these applications. Of course, these have nothing to do with 6G specifically. They can be used to any kind of networks that you're building today and for which you can pour the algorithms. I'm going to give you a couple of examples where the results are quite interesting in terms of things. One of the things that people have been working a lot is what we call the massive MIMO pattern self-adaptation, and trying to find what is the right beam to use, as I was telling you before, and basically what kind of configuration you can do, especially for the tilting, when you want to do tilting. If you want to do that, suppose that you have a cellular system, small cell system, you have 10 small cells, each one has 10 configuration for tilting, then that makes 10 to the power of 10 possibilities of all the tilts. It's extremely complicated to optimize as a system, okay? And it's extremely complicated to optimize because if one antenna tilts in one direction, the other tilts in the same direction, you get interference. It doesn't improve your system, okay? And so, of course, using AI is very nice because you have already a couple of performance metrics that you got for different configuration. Once you gather that data, you can automatically find a new one. And these are the things that we've been looking at, working on in terms of speeding up how you can do these small cells adaptation that I was talking about. Same thing for edge AI in terms of improvement. As you know, optimizing at the edge of the different, I would say, system makes it quite complicated in terms of that. And you can see you improve with coverage, throughput, and also power consumption using these techniques. There's also all the problems of revisiting the problems of fingerprinting. As you all know, fingerprinting in terms of localization is how do you localize based on what we call the signature or the electromagnetic signature of a device. Usually this is done by extremely complicated techniques where you gather a lot of data and you try to find for a new position or a new, electromagnetic signature, what would be the new position. My colleagues have been working a lot on these things and showcasing a lot of gains and especially also what we call a lot of consistent gains or persistent gains. What it means persistent is that when you gather a lot of data for a given configuration and you have a new electromagnetic signature, it's quite easy to find back the position based on all the other mapping of position. However, if the environment changes, then you're a bit stuck because you need to relearn every time. And so using what we call persistent techniques enables you that even if you have a bit of change in your system, you're still able to get some persistent information, which is still lies on those domains. And there you can see a lot of work of colleagues of mine like Maxime Guillot, Abdelatif Zaidi, and others who have been working on these techniques related to localization. Another thing also I want to mention is when you go up to the clear physical layer that I was saying, a lot of AI also for network or for wireless is also being used to improve basically the complexity of decoder or the encoder. And especially in the decoding realm, it becomes a bit nasty on the decoder computational complexity. So you don't gain necessarily in terms of performance, but you have a drastic gain in terms of basic number of computation that you need to do to decode a specific system with respect to the classical way of decoding because of all the things that you have to calculate. On the encoder side, it's also a big issue, and you have also a lot of work which is being done today to try to construct directly codes using AI techniques or machine learning techniques. By the way, I'm sorry to mix every time AI, machine learning, deep learning. Of course, AI, deep learning is a subset of machine learning. I didn't want to do a course on that. And machine learning is a subset of AI, okay? And we can, of course, classify them more neatly, but I'm mixing them quite rapidly because that was not a purpose of going specifically on a course on AI. And of course, also learning those codes, you can see a lot of papers being done today on optimizing some new types of codes for new kinds of environments of doing that. You have also everything which is related to scheduling and resource allocation. This is typically a case where feedback is used in general communication. Feedback has been used already in 3G, you know, but however, never exploit this notion of multi-agent or agent learning. And now you have a lot of work. I worked also on that, on basically building some deep reinforcement learning, basically for resource allocation, where you give a certain target in terms of quality in the point-to-point setting, multiple access setting, in the broadcast setting, the multi-cell setting, and you have depending on your kind of metrics, stuff like that, a lot of different algorithms which is used, if it's centralized, if it's not centralized, and things like that. If you want to do something more distributed between base station and things like that, which are using this concept of data that you generate and you learn every time. Let's go on the last part for the time I have, although I'm taking much more time than expected, is about, which I think is the most important thing. I think what I showed you before on the AI for networks, you will have gains, but you will not have what I call the 10x gain, the 100x gain that everybody dreams about. You will have, of course, 50%, 100, 200% improvements in your performance system using AI for networks. But I think where there's going to be a huge game changer is going to be mostly about what I call here networks for AI, meaning what are basically the new types of communication protocols that we need to build when we need to connect intelligence. And this is also where there's room for building new systems, where there's room for building basically a new kind of standard, where basically you will give also the kind of interfaces with which these systems need to talk. For example, if you want to build a 6G system, it would make sense in that realm that you would build it for that, where the notion of new protocols and how you do it will be a big game changer. And so, of course, the first question you have to ask yourself is that if you start doing that, and you start building a network that has AI, is what is the right architecture? And of course, this depends drastically on basically the kind of requirements that you have. There is many reasons why AI would run directly on the edge and would not directly run on the cloud. Because everything I was talking even before means that you gather the data, you bring it in a very centralized place, and then you run all the techniques that I was talking about in terms of how you learn and configure your system. But there's many reasons why you can't do that. One of the first reasons is basically latency. You have many cases, look at autonomous car, where the data you have gathered cannot be taken back to the base station for which you take a decision and come back. You need to take a decision locally, okay? Second is coverage. Sometimes you're not covered. You're taking a picture in the forest, you're going to walk hiking. While there, basically, things have to run locally and cannot run basically directly on a central server. The third one also, which is extremely important, is privacy issues. You have a lot of privacy issues where people do not want to have their data. So what I mean by that is that you have for sure a system will be more pervasive in having its AI, where AI is going to be on the device, where it's going to be on the edge, and where it's going to be on the cloud. And then you need to find basically the right way to exchange some kind of federated learning between the different entities so that you can agree basically on a model that has been learned globally, okay? Of course, today, a lot of people are trying to solve this problem through what I call the distributed AI framework, okay? In the sense that people are saying, okay, on the devices, because of privacy, the data cannot be exported. So I will try to learn the model based on the few data that I have. And I'm going to export basically the model that I have learned, which are the weights and basically the number of layers. My neighbor, which is also in a cell, will also do the same and will export his model. And all the devices will do that. And then basically all the models will go to the base station. I will not have the data which goes out, but only the model. I will do some kind of what we call meta model, and then I will broadcast that meta model for all the users. And from time to time, I will update to get these things. This is one way of doing it. In general, these kind of things do not scale, meaning when you have 1 million devices, sending that, if you do it in a TDMA manner, will take you time. If you don't do it in an orthogonal but non-orthogonal, you have this problem of quality of service, or basically in terms of reliability that you can transmit. And so it poses a lot of problem in how you do it. Other problem also that you'll be running cannot be the same as the one you're doing in the cloud. If you're doing on a device level, you have mostly consumption problem. Once you start having consumption problem, doing basically the kind of weights which full precision cost you a lot, then you have to go to what we call low precision AI, on which basically the weights, for example, can only take binary levels, 0 and 1, because you want to go down in terms of precision and consumption. But once you start doing some kind of what we call binary neural networks, you get stuck with the problem of how you do learning, when basically the weights can only take 0 and 1 values. Because learning, by the way, maybe I didn't say it, but whenever you do learning, it means basically that you start optimizing the function. And optimizing the function, you use basically a derivative. It's a gradient descent algorithm that you do. If you do a derivative in continuous, it makes sense, but whenever you have discrete and you have only 0 and 1, it's not possible. Then you need to look completely at the problem of redesigning a way of how you compute all these functions when you start doing this. So it opens, of course, the gates for very interesting problems for all the people who have been doing, for example, optimization in combinatorics. And if, for example, decoding is exactly one case. When we do decoding, we do nothing else than maximum likelihood, for example, is optimization in with 0 and 1s. And of course, the gates are quite open to find all the heuristics, which enables you not to be so far. And I think this is quite important because many players are moving towards providing more and more these kind of chipsets, which will be nearly everywhere, and for which we need to build up basically how they can connect between them. This is typically the kind of chipsets that are being built by a company like Huawei, but you have others who are also doing that. And as you can see, each one has its own processing power and also its constraints, and for which you need to globally federate all that knowledge. And again, if you look at, for us today, we're mostly on a current cloud and AI perspective, where in a 5G perspective, this is what you would do. It would be more centralized AI. You would bring and you work it out. And for which I told you, many of the KPIs of 5G would not be met because of the problem of latency, ultra reliable, low latency communication, and for which you would need to move to something which is more what I'm putting here: terminal AI, site AI, edge AI, and cloud AI perspective. And how basically, and what are the different types of information that you need to transit between the different layers is extremely important to build up this architecture. And by architecture, of course, there's two things. There's the algorithmic part, and there's the protocol part. So if you see today, we're nearly in the classical AI. This is a paper that we did recently with not recently, 1 or 2 years ago with the Mehdi, which was published in the proceedings, Mehdi Benis, in the proceedings of the IEEE, and looking at how you do distributed intelligence. Today, basically, we're trying to move to this notion of federated AI, and for which basically there's a lot of work being built around that with different mechanisms. And of course, the future is really about having this, what I call multi-agent reinforcement learning system, where you have really a collaborative AI. And this collaborative AI, of course, will still take a bit of time, because you need to prove also a lot of things on top of the algorithm, meaning that it will always work. You need to prove basically you have a convergence of the system. And today you have many people trying to work out this MARL feature, multi-agent reinforcement learning, through techniques related to mean field games. I worked a couple of years on that. I'm still working on that, by the way, but other techniques also to start trying to solve how you can do that. I think I gave you rapidly the two aspects which I think are quite important for this perspective, where you have AI for a better network, and I showed you a subcouple of cases that you can use, and then the thing which I think will be the big thing in the future, which is going to be about the network for a better AI, and for which we as engineers need to build the next generation network for machines and how they communicate. I just want to mention a last point, which is also extremely important. At this stage, when I was talking about AI, I was still talking about even connecting AI on things which are implementing DNN algorithms. I told you there is the issue of this level B communication, because machines will be able to reason. And by that, basically, the kind of communication that you do when you have reasoning, which is embedded in those machines, and not anymore just learning, but also reasoning. So it's mostly about native AI reasoning networks, not native AI learning networks. You start building, I told you, a context, and for which basically semantics is involved. Today, there's a lot of people working in different directions. I'm also working on that with my colleague Mehdi Benis. We wrote a recent paper that will be on arXiv by tomorrow or after tomorrow, called Semantics, Native Communication with Contextual Reasoning, that you can take a look at, and which will give you also the ingredients of what I call not anymore native AI networks, but semantics native networks, and for which you can now find a couple of papers trying to solve this issue of embedding semantics in networks, and for which, of course, the notion of capacity is not important anymore, because when you talk to somebody, it's not anymore how much bits you can transmit. Is to be sure that what you said is understood, okay, and not reconstructed. Make the difference between being said and reconstructed. This is normal when it's a device which is dumb. But when you want to transmit some information to a person which has also a capability of reasoning, you want to be sure that it's understood. And by that, you need to change the concept of capacity to something which is called semantic information, and for which you have also some semantic rate that you need to define. My colleague Jean-Claude Belfiore, for example, has published a paper on arXiv, which looks exactly at these notions of semantic information and being able to define it using a mathematical theory called topos. I think I'll finish here. I gave a lot of different, I would say, lines of research for all of you, and I hope it was interesting.
Okay, thank you very much, Merwan, for your very informative presentation. Okay, actually, I enjoyed it a lot, mainly when it started with the historical timeline behind AI. I think it's very important we know the origins of this very promising technology. We have some questions in the KI box. Okay. Before asking those questions, let me ask you I think the most simplest question is how can you define in very a few words native AI networks?
Yeah. So native AI networks, I gave here. I don't know if I can show it. Okay, I don't know. Okay, I don't have it here. But okay, in any case, bluntly speaking, is mostly about the fact that you have AI embedded in each part of the network. This is what I call native AI networks, and for which you need basically to use AI for improving the performance of a system which has AI embedded on each part of the network, and for which you need also to provide the networking capability to connect these AIs. These are the two parts. This is what my
Okay.
definition of native AI.
Okay, great. This is also I had in mind. Actually, I started to read many papers about this topic. It's a very interesting, definitely. And okay, I will go through some questions in KI box. We have a question from Nadia. She asks us about can AI technique go over explore and exploit phases in the case you have an environment which completely change drastically? And with yes, how can the model can be generalized?
Yeah, it can, but the problem in general, when you start using, let's say, learning in an environment with changes, then you need to reduce basically the scope of what you need to learn. So if you change, the more drastic changes you have, the more you reduce the scope of your learning. So let's say the following: suppose you have a system where you have a landscape of a lot of base station to learn and basically learn all the parameters. If your system changes, then you will reduce it to a single cell and do it only on the cell level. If the changes are not drastic, then you can explore much more parameters and increase basically the dimension of your system so that you have time to explore, to exploit. So it's roughly, if you look at what we call the time scale, which is like a block fading, if it's not the good model, but suppose you have a block fading, then in general, of course, your exploitation phase has to be a certain percentage of that. If it's too minimum, then you're not gaining if the exploration is 90%. And so what you need to be sure is to configure so that the exploration is very low. And for that, to be sure that exploration is very low, you need to reduce the dimension. The performance will be reduced for sure, okay? Because if you reduce the exploration phase, then it means basically that the number of parameters that it will learn is not big enough, and so you will not have. It's typically the same as you. For example, suppose that, just to give you an example, you have an exam in 2 days, okay? If you have an exam in 1 month, the number of topics you can study at home can be much larger because basically you have time to study all the things and be sure that the exam, you have all the topics which have been studied. Now, if you tell me that you have an exam tomorrow, you'll be very opportunistic. You'll make a decision in saying, I will only study maths and chemistry, hoping that maths or chemistry will come at the exam. If it doesn't, then I lose a lot. If they come, then I gain. And so you need to reduce basically the scope of what you need to study in that case. So in communication, this is what we do. However, knowing, which is this opportunistic part, what is the scope that you will explore is not easy because basically you take a risk. Okay?
Okay, thank you. The next question is from Mitun. His question is, in Edge AI, the frequency of updating the model parameters will play an important role. Obviously, it depends on the capacity. Do you have any thought on this?
So this is a very good question. In this, so this is what basically standardization will do. I was talking before about on the network for AI. If you want to implement, for example, federated learning, and you want to go to the standardization, this is the typical question that people will ask you: is how many times will you do it, depending on the needs of your network? And so, if you want to update mostly about image recognition or update, for example, an RSSI improvement, this will have an impact. And so this is where you need to think about the trade-off, is that the more you update, then the more, of course, you spend resources in exchanging with the network on all the different information. The less you do, the least you have an updated information. And so you need to find the right compromise depending basically on your quality of service that you want to have. So if it's, like you said, localization parameter, if it's basically capacity, bit rate will be totally different in terms of what you'd have to do. So of course, as a standard, we need to come up with a more generic way, because the idea of a standard is that people will ping that interface and be able to access that information. So if you don't give them too often the possibility, you don't open the gates to new innovation that people could exploit, because your big idea is that once you have the ability to ping at one point in the network, you could think of new ideas on how to exploit that information for better stuff. I don't know, sensing, for example, things that we never imagined.
Okay, thank you. Another question is, will the terminal AI interact with the cloud AI? Please
Yes, it has
elaborate.
to. It has, because basically you need to do a global learning. So now the big thing is that today the way the terminal does is that it sends all the data to the cloud, and then the cloud processes the AI. Here, the terminal does not send the data. It sends the model learn based on the small subset of data it has. I don't know if I'm clear. So you just send the model you learn. And then on the cloud, it will exploit all the models to do some kind of meta model, which will improve based on the different local data that they have. So it doesn't need the data, it just needs the model. So this is the kind of interaction you'll be doing, is exchanging models between the different, I would say, units in the network.
This is like a federated learning, right?
So federated learning is one possibility. You have many other ways of doing distributed AI. Of course, federated learning is based on updating models. Yes.
Okay. Okay, any more question? Okay, another question is, what part in machine learning can be standardized in 3GPP?
So machine learning cannot be standardized because it's an algorithm. However, what you will standardize is the interfaces. How often are you going to exchange and ping? What are you going to exchange? The models, the weights, what is the granularity? Is it going to be on 2 bits, 6 bits, 8 bits? If you change weights and the weights are not with full precision but very rough, then you would need basically to reconstruct something which is not going to be accurate, and you'll have some problems. So it's mostly about not the machine learning part, but how the interactions of the different, I would say, AI are discussing. This is what you can standardize. But AI cannot be standardized by itself. It's just the interaction.
Okay, due to the advanced time, I will ask we have more 2 questions, okay? And,
Okay.
Okay, the next question is, would it be possible for standardization to impact on accuracy requirements on convergence in case of federated learning?
Yes, it can, of course, because exactly what I'm saying is that depending on this kind of quantization that you're going to do on the weights, on the information, and how often, it will have an impact. And then same thing, the time scale at which you're going to do can have an impact. But it doesn't mean that standardization will showcase convergence. It can enhance the convergence, but as I told you, on a distributed setting, we still don't have a full understanding of how and when the system converges. And this is, I gave you at the beginning an example in the SON realm, the self-organized network realm, where basically already there, depending on the functions that you want to optimize, if it's an expected rate or instantaneous rate, you have basically different outcomes that can happen. And so to make it short, what I'm saying, it will have an impact, but it will not ensure the convergence.
Okay, thank you. The last question is from Professor Rodolfo, is regarding the use of AI techniques for distributed networks, right, where one of the goals is, for example, enforce a given game theory equilibrium. What are the most promising AI techniques?
Okay, so that's a very good question which is posed. So today, of course, one of the things that people are using is what we call multi-agent deep reinforcement learning, which is one of the promising approaches which is being used for a system to enhance its convergence and attain equilibrium. So the idea is that you use the ideas of reinforcement learning, but also exploit through a Markov process the data that you have embedded in the past and be able to trigger both. So that's one of the directions. there are, of course, other ways of looking at the problem, but this one for today is one of the things that we're seeing being pushed.
Can
Okay.
I ask one last question?
Yes,
Yes.
Dr. Wong, go ahead.
You mentioned you don't trust the black box approach of AI techniques.
Yes.
And there's some approach about machine learning operations where we keep track of every step of data preparation and when to train and how to optimize the parameters. What do you think about this machine learning operation approach? Is it the solution to the AI trustworthy AI problem?
So it's one step forward, but it's still far away. So when I said to before is that it's not the question I don't trust. I think that communication engineers in general have models which work. And so I had a hard understanding of why you would throw out all the legacy of more than 70 years since Shannon of work where people know what is an AWGN channel, know what is a relay channel, things like that, to throw everything and start doing, for example, beamforming without trying to understand what is the wireless link. Okay, because today somebody can do beamforming without understanding. You can come up with a type of precoder without understanding what is basically signal processing today. And so for me, that was for sure a wrong approach because you need to understand. And the black box is not just necessarily about the steps. It's also basically the fact that when you generate based on the data, to be able to ensure that it works, you need to make assumption on the data. And therefore, you don't know exactly what are the assumptions you made. And it will depend also on the function that you need to approximate for which you have no clue. And so it poses a big problem. Let me give you an example. On the kind of problem that I was of kicking the ball. Suppose that the data that you got of kicking the ball was only at 1 meter, 2 meter, 3 meter, 4 meter, 5 meter, and it was super sampled at the beginning and very largely sampled after. Then the reliability you have on kicking the ball very far is not going to be as good as the one kicking in the beginning, because there you have a lot of data which sampled, and so your approximation is going to be very good. Whereas there, it's not going to be good. And so there, I cannot give you any kind of reliability on the results of the beam I have because I have no clue on how it was sampled. So you need a lot of approximation, and this depends also on the function that you want to approximate, and for which you need to already to make some modeling and assumption. And so if you don't do anything, then of course you come up with a black box and you have no clue. So it's not just about processing, of being sure that the data is clean, things like that. It's also being able to have an understanding that the function you want or the goal you want, you can analyze it and have some kind of definition of what it is, make some assumption on its properties, on its continuous, and it's not too bumpy or something like that.
Okay, thank you very much.
Yeah.
Okay, thank you once again, all the attendants. And a special thanks to Merwane for giving this speech. It was very, very, very informative, and we still hope that we can start some interactions. We are welcome here at EUTech, okay? And so I would like to inform that our next webinar will be 2 weeks from now. So please keep an eye on it. It will be presented by Dr. Shao Wen from Singapore University of Technology and Design. Okay, and I will start advertising through some mail leads and research groups. Okay, so thank you everyone. Thank you once again.
Thank you for your time, and it was a great time to spend with you. And if you have questions, just drop me an email. And I'm quite sure that in the next 2 or 3 years, we'll see a lot of things going on
Sure.
those different directions I was mentioning.
Thank you.
Thank you very much. Thank you. Bye-bye.
Take care.
Hi, Medwan. This is Tao.
Hi, Tao.
So
How
very
you doing?
nice talk. Yeah, very interesting. So you are in Abu Dhabi, right?
I am in Abu Dhabi, not in Adoub yet.
Yeah. Oh, yeah.